Okay, off we go. So real quick before we get back into the math, and then I deleted it. So I sent out an email about this. I just want to make sure everybody saw it. So I finally got around to realizing I should have got this a long time ago, but super easy for me to create a new copy of the content syllabus that shows the topics we're covering in actual class chronological order, so thus showing that we're doing 1.6 first. I don't know why I didn't think of this before. It's never occurred to me. Anyway, make sure that you're aware of this. I encourage you to just use this instead of the course website content syllabus because all the exact same information's there. This just has it in the order that's relevant to our sections. So please use this. One thing you'll notice is that after 2.4 that we're going to finish today, 3.1 is next, and then 2.5. And the reason for that is because 3.1 has some ideas that are actually, I think, really useful in 2.5, and I don't want to have to handicap myself in not being able to use this. So, okay, anyway, heads up, make sure that's there. Make sure you know that that's there, and I encourage you to use that as your reference. And off to the material. So we were talking about higher order partials. And remember the big idea is that when you take a partial, you notice the partial is also a function of all the same variables. And so you can just as well talk about its x partial and its y partial, etc. And last time we talked about the different notations, and there's this unfortunate reality that this notation and this notation kind of look like they're doing the x and y partials in the opposite order, but they're not. They're actually the same order, and this is just a consequence of arbitrary, unfortunate notational convention. So anyway, that's where we left off last time. So you will notice here that this and this are equal. What are the odds? Well, it turns out the odds are actually pretty good. In fact, for sufficiently nice functions, this always happens. Now, not always, but for sufficiently nice functions. So I need to be clear on what I mean by sufficiently nice functions. What we need is to know that the kth order partials all exist and are all continuous. Now, it does seem silly to note a convenient statement about higher order partials that you can only conclude if you've already computed the higher order partials. Yes, that is seemingly pointless. But very often, this is a lot easier to observe than requiring actually computing them. So, for example, you take a polynomial here. Right? Any polynomial, in fact. If you think about it, polynomials, it's pretty clear when you take the partials, still a polynomial. And their partials, therefore, will still be polynomials. And so all of the higher order partials will, of course, be polynomials, and those are all continuous. And so we can conclude what we need to confirm this condition that all the kth order partials exist and are continuous, even if we don't compute any of them, just because we notice something really nice about the form of the function. Okay, so now specifically the notation for this, if you want to conclude something about kth order partials, then you need the function to be ck, which means you have to check up to the kth order partials. And so that superscript in the notation there is an indication of how many partials you need to check. And the C in the notation is a reference that not only do I need them to exist, but I also need for them to be continuous. So it's a pretty reasonable notation, actually. And anyway, you may have seen this in a Calc 1 class at some point. Maybe not. Doesn't matter. Okay, when this happens, if your function is ck, then you get this lovely conclusion that it doesn't matter which order you take the partials. You can do xy or yx, whatever, it's all the same. Yes?
Could you repeat y?
I haven't. Oh, I'm not going to prove this.
Oh,
Yeah, no. Proving this is hard.
Okay.
Yeah. So now, please don't be disturbed by the notation here. This looks like a scary statement. All this is a fancy way of writing down that these are the same partial derivatives, just done in a different order. And so the big idea is that you'll notice that these subscripts down here are numbers which I'm just claiming need to be rearrangements of each other. So again, fancy notation for do the partials in whatever order you like. Okay, next thing we want to talk about, what do these higher order partials look like? Right, and again, if you want to use something, you have to have some sort of foot in the door of how it connects to the real world, or what it looks like geometrically, or something. Otherwise, it's just sort of algebraic games for no particular purpose. Right? So what do these look like? I'm going to restrict our attention to graphs. Again, very important. Make sure that you have these partitions in your mind, right, separating the calculus of graphs from the calculus of level sets, etc. Right? So the geometric interpretations you make will depend very much on what kind of picture you're actually looking at. So here we're going to focus on graphs. And this first business is actually, I'm going to call it really good news. It's exactly what we would kind of expect. Let's think, for example, about FYY. Yeah, just because. Right, this says we're taking the partial with respect to y, and then we're taking the partial with respect to y of that. Notice that for both of those calculations, the first y partial and the second y partial, x is constant. Right? So for that entire calculation, we're going to be looking only at this plane that has some fixed value of x. At which point we're looking at a single variable function, just what you get when you take this cross section of that Pringle, and that cross section is a curve. That curve is the graph of literally the single variable function that we're going to be taking the derivative of. So what is FYY? Well, we're looking at that curve, that cross-section curve. We're taking its second derivative. And y'all already know when you're looking at a single variable function, in fact, the graph of a single variable function, second derivative just means concavity. Right? So this is clearly concave up, as I have it drawn. FYY is positive. So that's the geometric interpretation there. There's a highly analogous interpretation of fxx, in which case, of course, y is constant, which means we're looking at basically that line, clearly concave down. Fxx is negative. Everybody good with that? Yeah.
So for fxx, you're setting x equal to like a, and then you're creating the.
Yep, that gives you a single variable function, and then you're just taking the regular second derivative. Yeah. Right. Okay, here's where it gets weird. I'm going to say this is basically expected, right? Second derivatives, concavity, yawn, right? Come on, this is exactly what it was in Calc 1. Okay, here's where there is no flashback to Calc 1. What if we're looking at a mixed second partial? Again, there is no such thing. There is nothing even vaguely analogous to this in single variable calculus. So we're in uncharted territory here, and there's a way of doing this. You got to look at this just the right way. I'm sure there's probably other points of view. This is my favorite. Let me try to get this all onto the page. When I drew this figure, the very first thing I did is I drew a figure where I had an actual surface, and then I drew the various cross-section planes and tangent lines and blah, blah. And frankly, the figure just got really nasty. It really just busy and distracting and confusing. So I decided that this is easier to work with without actually drawing the underlying surface. Right? So all I'm going to say is that these are tangent lines to the underlying surface, specifically in the directions indicated by these shadows down here. And you can kind of use your imagination and visualize what the underlying surface is. And so I think this is, believe it or not, I think this is actually better. Sometimes this happens. Sometimes when you're drawing a diagram, less is more. This is one of those times. Okay, all right, so let's start making the connections. How am I going to visualize the partial of f with respect to y? Well, okay, that means we're going in the y direction, such as, for example, if I were here, then this is the y direction. I'm going to look at the tangent line to the surface in that y direction, and I'm going to look at the slope of that line. That's the y partial. Now, I can do the same thing at various other points. These are all just at different points looking at tangent lines in the y direction. Again, just at different points. So these are what the y partials look like at various different points. Fine, no sweat. Here's the weird part. Let's try to ask, how would I understand the x partial of that y partial? Don't step on the landmine. It's tempting to say the x partial is the slope of the graph. We're not looking at the graph of the thing we're taking the x partial of. The thing we're taking the x partial of is the y partial of f. Z is not equal to the y partial of f. Z is f. The y partial of f is something different. So if I want to understand the x partial of this y partial, I can't make any reference to slopes of cross sections in the x direction because I'm not looking at that particular graph. So I can, however, take a different point of view on what a partial derivative is. And you all will recall this point of view from when we were talking about the sort of, what did I call it? The literal picture of a function, right? And when you're talking about the literal picture, then you move in the direction indicated and ask how fast is the function changing. So that's what I can do here. I can say, look, here's me moving in the x direction. And as I move in the x direction, I can ask, how fast are these slopes? How fast are these slopes changing? And now let's just kind of think it through a geometric appeal here. I feel like the one in the back, I feel like that slope's about -2, ballpark, right? It's negative, right? -2 is what I'm going to say. This one's about -1. That one's about -0.5. Here it's about 0. Here it's about +0.5 or something. And so what is happening as I move as I come out of the page, right? As I move in the x direction, the y partials that I'm taking the x partials of started negative and were consistently increasing. I think the rate of change is positive because they were going from less to more. Everybody see that? So as I have it drawn here, in this case, right, looking at this picture, I think that this x partial of the y partial is positive. So that's how you make that geometric interpretation of the mixed partial. It is a little tricky. The little summary that you would make of this, is this about concavity? No, it's just not. Right? That's not a picture of concavity. I feel like what it is it's a twisting. Right? Like imagine that. I keep thinking I'm going to be able to find such a thing, but I would love to have a little square sheet of rubber about this big, right? And then holding a square sheet of rubber, be twisting it about like this. And that's something you can do with surfaces. Surfaces can have a twist in them. Curves can't. Curves just, it doesn't make any sense for a curve, right? But for a surface, you can twist it, and this is a measurement of how much you're twisting it. Yeah?
Where would the x arrow point?
Where would the what now?
Like the partial over dx arrow point.
Well, so partial with respect to x says as I go in the x direction, right, and here's the x-axis. So here's me going in the x direction, what I have indicated in blue here, right? And that represents me going in the x direction, and x partial says how much does this thing change as I move in that x direction.
Well, I meant for that one. Like, would you be able to tell? Or?
I don't understand what you're asking. I'm sorry.
Oh, like the arrow, the blue arrow. Like where would that one be? And for that dimension.
Again, I think I must be misunderstanding. You're asking me which direction this blue arrow is pointing?
No.
I'm sorry.
I'll ask you after class.
Yeah. Good. Okay. All right. Okay. So, side note, real quick. This is called torsion. That's just a word, and again, more intuitively, I think of this as a twisting of the graph. Okay. So let's talk about parametric curves. Y'all remember parametric curves? I'm sure. This is what the parametrization looks like. Position as a function of a single parameter. That single parameter we typically think of as being time, right? Okay. And one coordinate at a time. You can write it like this if you like. Okay. All right. Okay. So let's talk about how to take the derivative of such a function. Now you're going to notice that there is a single input variable here, and y'all remember the derivative matrix, right? And there's rules for how you organize the derivative matrix. The columns correspond to input variables, the rows correspond to output variables. Here we have one input variable. That means our derivative matrix has one column. And I'll tell you another thing. There's only one input variable. When you take derivatives with respect to, well, there's only one variable, I don't even have to say partial derivative. There's only one variable. There are no other variables to hold constant. So this is not a typo. These are literally Calc 1 derivatives, just plain old derivatives of the coordinate functions for the parameterization. Okay, all right. Now, reminder, when you have a single variable function, which, by the way, we do, again, can't emphasize enough, right? This is a single variable function, vector valued. Yeah. But single variable function, we already have a formula for how to take a derivative. Calc 1. This is how you take the derivative of a single variable function. And nothing to it. And I argue that what you get when you take this single variable derivative is computed one coordinate at a time. Let's look again at this formula. How do I subtract two vectors? One coordinate at a time. How do I divide by a scalar? One coordinate at a time. How do I take a limit? Okay, we didn't really talk about that, but I'm going to assert, I think this is believable, I hope you'll trust me. When you take a limit of a vector-valued function, you do so one coordinate at a time. So, in fact, our old Calc 1 definition of a derivative actually gives us, when you take those derivatives one coordinate at a time, it actually gives us the exact same thing that the derivative matrix does. That's kind of a cool observation. Okay, said differently, I have an interpretation now of how to geometrically visualize my derivative matrix for a parameterization, for a parametric curve. And that's this formula right here. Now let's just think this through. If I have a parametric curve, such as, let's say about like that, how do I subtract 2 points on that curve? Well, the first point is, let's say, about like that, and the second point is, let's say, about like that, and I subtract by, tail to head. That's how you subtract vectors. Is that cool? Okay, so that's the subtraction. Let me clean up my picture a little bit. That's that difference there. What happens when I, let's see here, I'll do it like this. What happens when I divide by h? Well, when you divide by h, the direction doesn't change. I just get a different magnitude. So maybe something like that. Okay, and now the question where we have to sort of think a little bit intuitively, what happens when I take a limit? So what happens as this point gets closer and closer and closer? H getting smaller and smaller means I'm getting closer and closer along this curve. And a geometric appeal, two things happen. On the one hand, these blue vectors get shorter and shorter, while of course my denominators get smaller and smaller. So in terms of magnitude, it's unclear. They're not exactly clear what's going to happen there. You kind of expect probably that those shrinking numerator and shrinking denominator would probably roughly cancel out, and that's approximately true. The other thing that happens, though, is that the direction, let's see, let me highlight this, the direction that these vectors are pointing, you get that, and then for a closer point, you get about like that, and as it gets closer, it gets more like this, and then in the limit, you would expect to have a tangent. Oh, that's not a good tangent line. You would expect to get a come on, do better than that. There we go. You'd expect it to be approximately a tangent line. Yep.
So is x a vector?
Yeah, that's right. X is a point on the parametric curve. That's right. It's vector valued. We're thinking of them as points, but yeah, they are also vectors.
Is it also a function of t?
Yep, that's right. So position is a function of t. That's right. That's what a parametric curve is.
Then what is t?
I like to think of it as time. It's any parameter, any input variable. I think it's most convenient to think of it as time.
I don't quite get it.
Okay, so that's a pretty open-ended question. So how about we talk about that after class?
Okay.
Yeah. So parametric curves is a whole discussion. In other words, that's something we talked about for a while. Yeah. Okay. Okay. So let's think about what can we say then about this eventual derivative. And the first observation that we just made is that it's in the direction of the tangent line. So that means the derivative vector points in the direction that your parametric curve is going. It points in the direction of motion. You're thinking of t as time, thinking of position changing as a function of time, that's a motion, and x prime points in whatever direction the curve is going. Okay, next, what is the magnitude, right? How long is this derivative vector? And the easy way to see this, I think, is that you notice this numerator is basically a distance. This numerator, well, it's a displacement vector, but if I take the magnitude, if I'm interested in the magnitude of the velocity, take the magnitude of that numerator, that's a distance. And h, my denominator, is the difference between the time here and the time there. So this is elapsed time. So the magnitude of the derivative vector is literally distance per unit time, and that's speed. Wrong color. That's speed. Okay. So here's the great news. We already have a word for this. The vector that points in the direction you're going and whose magnitude is the speed, lucky break, that is literally the definition of velocity. So this is our big conclusion then about the derivative of a parameterization. Whoops. Come on. There we go. The derivative of a parameterization is the velocity of the parametric curve. Yeah.
Oh, how'd you say? So you're just saying h is like we can think of as
It's an elapsed time, right? So we start off looking at time t, and then now we're going to look at a subsequent point at time t plus h. So it's a time h later. So yeah. Okay. Yeah.
I don't really understand the notation in 2. So you took the magnitude of the numerator and then divided that by h, which is simply t.
Mm-hmm. Yeah.
But can you just maybe explain the notation before the equals sign? So what
Here?
is x?
Yeah. So right. So this x prime is the derivative that we're interested in, right? And this just says that we're looking at the magnitude of that. So we're trying to take the magnitude of that velocity vector. And when you're taking the magnitude, well, you'd need to take the magnitude of the numerator. Technically, I'd need the absolute value of the denominator. But yeah, right.
Thank you.
Yeah, sure. Okay, so I hope this is actually, in fact, kind of familiar. There's a single variable version of this. This is totally analogous to something y'all saw in Calc 1. And there's a whole category of questions in Calc 1 where they tell you about, well, you've got this car and it's driving along a road and you know what the velocity is as a function of time. You want to sort of compute how far it's driven, that kind of thing, right? So that is literally what they call x in examples like that. They're literally telling you position as a function of time. That is literally a parametric curve. It was a parametric curve on a line, so it doesn't seem like a curve, but it is. It's position as a function of time, and that's a curve, yeah.
Before it was limit as h approaches 0, but then you see how the second bullet point.
Yeah.
The limit. What's that limit like?
Yeah, so this is the idea of if you want to define instantaneous speed, you can't say, okay, well, I'm going to let a finite amount of time elapse and then just base your calculation on that, because the speed may change in between here, right? So the idea of taking a limit as h approaches 0 is that it's like we want to compute an average velocity, but over an increasingly shrinking interval where everything's pretty much increasingly the same, and then the average becomes the instantaneous. Yeah, right. Okay, so hopefully this is a recovery of single variable ideas that you'll recall from your Calc 1 classes. And by the way, totally analogous. Remember, the derivative of velocity is acceleration, and so that means that the second derivative of position is acceleration. Okay. All right, so now example. This example is super analogous to stuff that y'all have already done in single variable calculus classes. So I'm going to be kind of quick with this. We're given a velocity and an initial position, and we have two questions. What is acceleration as a function of time? What is position as a function of time? Right? And we're just going to use the results from the previous page. We know from the previous page that acceleration is the derivative of the velocity. And so I'm literally just going to take the derivative of that velocity, and you take the derivative one component at a time, as we just discussed. And those are easy derivatives. By the way, real quick reminder, I am assuming that y'all are strong with all of your single variable differentiation. There's a bunch of things to know: product rule, quotient rule, chain rule, power rule, various trig rules. You've got to make sure that you're good with all that. Okay, next, how do we find position? Well, we got to kind of think through the semantics on this. If velocity is the derivative of position, then position is the antiderivative of velocity. Right? Okay. So with that in mind, position is the antiderivative of velocity. Again, velocity was given, so I'm just going to take its antiderivative. And again, you can do that one coordinate at a time, and these are not hard antiderivatives. But again, make sure you can do that kind of stuff. Again, Calc 2 is in the prerequisite trail for this course. So you got to make sure that you are good with all your Calc 2, what they call integration methods like integration by parts and substitutions and all of that jazz. Okay. All right. Now, don't forget your plus C. Right? That's right. Easy to forget.
Yeah.
Easy to forget. And one of my own little personal quibbles with mathematical convention, they call this the integration constant. I think that's really unfortunate. We're not computing an integral here. This is an antiderivative. That's what this means. This means antiderivative because there's no bounds indicated. There's no domain indicated. This is not an integral. It's an antiderivative. Right? Now, okay, who cares? Well, you'd be surprised. I mean, it's actually, this is an important distinction. And we're going to spend a bunch of time in this class talking about integrals. And they are conceptually very distinct from antiderivatives, right? For one thing, notice antiderivative is a function. Integrals are not. Integrals are values. That's pretty different. Right? Now, yes, closely related, fundamental theorem of calculus, yeah, fine, right? But nevertheless, different things. And when things are different, it's a good idea not to blur the distinction. Right? So, anyway. All right, now my next little soapbox speech related to this is that I see the following happen just very commonly. And the bigger deal I make out of it, the less it happens. So that's why I'm about to make a big deal out of it. So many students on exams in this class seem to think that their integration constant, there I am using the conventional term, is always equal to the initial condition. That is absolutely not true. It's just not true. Straight up false. Now, why do students think this? They think this because in their high school calculus classes or what have you, they always restricted their examples to this very narrow category of examples where it's only polynomials. And it turns out, for basically coincidental reasons, for polynomials, yeah, that'll work. If t equals 0 is when your initial condition is, and if these functions are all polynomials, yeah, that coincidentally happens to work. Still not good enough because, again, keep in mind, we're not interested in answers. We're interested in reasoning. And even for polynomials, this is not legitimate reasoning. Right? It's just not true as a broad statement. So here's what y'all need to do to evaluate the integration constant. Remember that we've got this statement. This is true for all values of t. So it must also be true for particular values of t. And I'm going to choose the value of t where I actually know the initial position, whatever value of t that is. Right? T equals 0 in this case. So you take that and you plug it in to this equation. And then let's see what happens. Well, x is 5, 6 when t is equal to 0. And this business right here, you plug in t equals 0. It turns out to be 3, 1. And now my purple equation, having plugged in t equals 0, my purple equation becomes this. And of course then the c that I'm trying to solve for, easily solved for by subtraction. And notice, not that. Does that make sense to everybody? So again, please don't step on that landmine and just be like, yeah, see, it's the thing. No. Wrong answer, probably. Wrong reasoning, definitely. Okay, let's see. I've already complained about all of this stuff, so I'm not going to repeat that. But let me also point out a very common misunderstanding is to call this an integral. I guess I've kind of complained about that a little bit already as well. So yeah, let me repeat. Not an integral. And so don't make any misinterpretations such as thinking about, shouldn't this be like area under a curve or something like that? No, absolutely not. Yeah. So there is a lot to say about multivariable integrals. This is not the time to get into all that. That's what chapter 5 is long discussion of multivariable integrals, and we'll get there eventually. Okay, real quick, as noted on the content syllabus, there's a bunch of stuff about Kepler's work in planetary motion that's in this section, and you're not responsible for it. It is in the excluded material column on the content syllabus. You don't have to mess with that stuff. But there is one theorem in there that is important and that you are responsible for. It's Proposition 1.4, they call it. This is pretty believable. It's a couple of product rules for when you have vector-valued functions of a single variable t, so what you're going to want to call parametric curves, but anyway, any two vector-valued functions of t, you want to take the time derivative of their product, be that dot product or cross product. Power rules both work. So, handy fact, not hard to prove. You can just write x and y in terms of coordinates. Write x as x1, x2, x3. Right? And then you can just literally multiply out this dot product. Literally take the time derivative using single variable calculus rules, and this is what pops out. So, not hard to prove. Make sure that you know these facts, though. Yeah.
So there's like behind the works of like using left linearity and like right linearity rules like, that you didn't show here. Is that like?
Sorry, I'm not understanding.
Like like when it's like C and then dot product between like V and W. And,
yeah.
Like, and then like you use like different rules. Like.
Are you wondering if that comes up in this calculation?
Yeah,
I don't think it does, but I can't quite do it in my head. I don't think that's going to come. If it comes up, you've got it.
Okay.
But I don't think it will.
Okay.
I could be wrong, but I don't think it will. Yeah. Right. Okay. Okay, so that's 3.1. I think 3.1 is a really useful tool to have in our toolbox for understanding the chain rule. We'll see why in just a couple of minutes. First thing I'm going to say is, I assume that y'all are strong with the single variable chain rule, right? Ancient history, Calc 1. Make sure you're good with that. There are various different ways to think about the chain rule. There are various different manifestations of the chain rule. I'm going to take a very particular point of view on the single variable chain rule. Very narrow, very specific. And I'm going to spend an entire page of notes talking about that specific point of view on the chain rule. And I just want to make sure we're clear on why I'm doing it. It's not because I don't think you know it, right? I assume that you know the single variable chain rule. The reason I want to spend time talking about the single variable chain rule is because it is this specific, narrow point of view on it that I think generalizes most naturally. Right? So what I'm doing here is not teaching you Calc 1. What I'm doing here is setting up an analogy that we'll be making on the next page. Okay, so here we go. Y'all remember there's different ways to think about the derivative. Here's my favorite, a derivative. Now, that's my favorite in this context. Derivative relates input velocity to output velocity, right? So we've made this observation. The derivative in this case is what you multiply by that to get that, right? Okay. So this is the way I want to think about derivatives in this, on this next couple of pages. By the way, just to be clear, this x prime here, this is a velocity. I've written it as x prime. I've written it as a derivative. That's because x is a function of time, and so x prime means derivative with respect to time. Okay. Whereas this is a derivative of y with respect to x. So I'm referring to this as the derivative, and I'm just going to refer to the t derivatives as being velocities, just to avoid that confusion. Okay, so that's the take I want to have on derivatives. Okay, with that in mind, let's now think about compositions. So this weird-looking picture here is nothing more than me composing two single variable functions. So, for example, here's a single variable function called f. X is the input, y is the output. Here's another single variable function G, Y is the input and Z is the output. All right, is everybody on board? Okay. There is a third single variable function in this picture. The third is the composition. The composition, oh gosh, color choices, is where X goes in and Z comes out. This is what you get when you kind of do them both together, all thought of as one single function. And so, X is the input and Z is the output. Okay. All right. So now, if I have these functions composed, if X is moving with some velocity, then of course that means Y is going to be moving with some velocity, and of course that means that Z will be moving with some velocities. And there's various different statements that I can write down about how these velocities relate to each other. And ultimately the chain rule is going to pop out as a consequence. So in particular, what's the relationship between X prime and Y prime? Well, that's what the derivative of f does. The derivative of f, dy dx, is what I multiply by green to get blue. Let me say that a little bit differently. It's the factor that I multiply by green to get blue. And that's what's written in this equation 1 down here. Equation 2, kind of the same thing. Equation 2 says that the derivative of g, dz dy, is the factor that I multiply by blue to get orange. Again, I'm just thinking of derivatives as factors, what I multiply by an input velocity to get an output velocity. And now I'm just going to make an intuitive appeal, and I think this is pretty believable. Forget about all this stuff here for the moment. Let's just think if I give you some number, and if I were to ask you, multiply that number by a factor of 2, and then if I were to, after that, say, okay, now multiply that by a factor of 3, altogether you've multiplied the original number by 2 times 3. Right, so factors multiply is the point. So when I ask, what do you get, or what is it that you multiply by x prime to get z prime? Well, on the one hand, the thing you multiply by x prime to get z prime is kind of by definition of a derivative. That's dz dx. But it's also the product of these individual factors that you sort of in succession could have used to compute z prime. So it's the product of dy dx times dz dy. So let's see here. I'm going to highlight like that. So lo and behold, chain rule pops out. Right? The fact that you can think of this in either of those two ways shows that this derivative has to be the product of these two derivatives. So that's how I like to think about the single variable chain rule. It is one of many, but I like this one because it generalizes really nicely, as we're about to see. Okay. By the way, if you want to see the algebra, if you don't trust this hand-waving argument I give about factors, one thing you can do is step 1, persuade yourself of these 3 statements that are all just statements about how derivatives work. This is what derivatives do. And then take this one, that's the formula for y prime, plug it into here where I have a y prime, take that formula for z prime and kind of multiply it out, and you get this. And then on the other hand, we have this other formula for z prime that comes by way of the composition, and altogether then, this and this tell me that that is equal to that, and that's the chain rule. So if you want to get all algebraic about it, that's how you do it. I think that's kind of, I think that's unnecessary. I think it's much easier to just understand derivatives of factors and factors multiply. Times 2 followed by times 3 is times 6. All right. So, and now before we do the analogy, I'll point out this nice little pithy little summary, and that is differentiation turns compositions into products. Notice that this is the derivative of a composition, and as you can see here, that is literally a product. Okay, all right. So, single variable calculus. Here's the multivariable equivalent. And before I do anything, let me just point out, see what that page looks like? Notice how that looks exactly like this page. I did this very much on purpose. I wanted to emphasize how truly analogous these arguments are. We interpret we interpret derivative, in this context, as a factor. We write it down as a composition. We observe that factors multiply, and we write down the result. And the exact same thing works in the multivariable setting. Now, though, the factor is a matrix. Right? Derivatives in a multivariable setting are matrices that you multiply by input velocities to get output velocities. And yeah, sure, so it's a matrix, yeah, fine, but whatever, it's a factor. And factors multiply. So when you compose like this, and you have an x prime vector and a y prime vector and a z prime vector, df is the factor that does that. dg is the factor that does that. When you do those together, you effectively multiply by the product of those two factors, which is what the derivative of the composition is. It's really very much the same idea. And so now again, you can go through the algebra, you can write down each of these equations and plug this into that and move things around. If you really want to see the algebra, you can do that. But I think it's a lot easier just to understand that factors multiply, and that's what this is saying right here. We can get this to come back up. The altogether factor that turns x prime into z prime is the product of the factor that turns x prime into y prime times the factor that turns y prime into z prime, right? A product of a succession of multiplicative factors is a product of those two factors. All right, so this is the multivariable chain rule, and again, you can think of this as differentiation turns a composition into a product. It's really very analogous. Okay, so there you go. Multivariable chain rule is a statement about how derivative matrices multiply. Okay, let's see. Last quick comment, and then we'll call it a day. Unfortunately, we're not going to have time to get to the big example, the first of many big examples. But I do want to confess that the picture I drew here has the limitation that space was merely two-dimensional, and this space was merely two-dimensional, and this space was merely two-dimensional. It would almost be enough to make you think that maybe my conclusion only makes sense in 2 dimensions. I mean, after all, right? But I'm going to point out, nowhere in this argument did I make any reference to these pictures being 2-dimensional. I could have made them 3-dimensional. Bam, now they're 3-dimensional. Right? Or I could make one of them 3-dimensional and the other two-dimensional. The argument's exactly the same. Right? And all of the business about which dimension for which space, that's all wrapped up inside of the shape of these matrices. Right? Derivative matrices always have exactly the number of columns necessary, exactly the number of rows necessary to do what they need to do to relate input velocity, output velocities of whatever dimensions they might happen to be. Right? So, yeah, my picture was only 2-dimensional, but it could have been any number of dimensions, and so our conclusion actually works for any number of dimensions. and I'm out of time. We'll call it a day there. See y'all on Friday. Have a good one. Don't forget about attendance if you came in after I finished attendance.